Welcome and thank you for joining us for today's workshop of cellular respiration. I'll be introducing your presenters in just a moment. I'd like to share a few housekeeping items before we get started. I want to let everybody know that in the chat, there should be a link to a shared Google Drive folder. If you didn't have a chance to download the handouts for today's session, they can be found in the Google Drive. We can also send those after the workshop as well. We'll also be sending out a certificate of attendance to those of you who are attending the live session today. And now I'd like to introduce to you our hosts, Colleen and Sarah.
Hello there.
Hi. So my name's Colleen McDaniel. I am a biology and environmental science specialist here at Vernier. And today we are going to be doing an activity looking at cellular respiration. Helping out, I have Dr. Sarah Tolarovic, who is going to be the one on the end answering any questions that might pop up in that Q&A section. To get started though, we would like to do a poll just to kind of see who's all attending right now. So Sarah's going to put up a poll for everyone to participate in. Just two questions. One, what level do you currently teach? And we're also kind of curious of what type of instruction you're currently doing. Is it in person? Is it a hybrid? Is it remote? Just kind of so we have an idea of what everyone's experience is right now. Okay, Sarah, does that look like everybody?
It looks like almost everybody. We have, looks like one person who hasn't responded yet. But we do have 12 responses. So it looks like we've got about, are you able to see the results, Colleen, or shall I read them to you?
I cannot.
Okay, so we've got 67% of our participants are high school, 17% are college, and 17% are other. And then it looks like our largest population are doing a hybrid mix. Okay. About 58%. We have one person doing 100% in-person classes, and it looks like 33% of our audience is doing 100% remote.
Okay, interesting mix. Fantastic. Thank you, Sarah. So today we're going to be kind of doing one basic exercise, but we're going to look at different variations on it. So primarily, I'm going to be concentrating on doing the cell respiration activity out of our Biology with Vernier lab book. And to do it, I'm going to be using our Go Direct CO2 and O2 gas sensors. So just to kind of give you some background on how we're going to be doing this is, for doing cell respiration, I'm going to change my camera here. The idea is that we're going to start with some peas that I have been soaking overnight so that it starts the germination process. And we're going to be putting some of those peas into a respiration chamber. Now, since I'm going to be doing two sensors, I'm going to be using what we call our BC250 chamber. And this is a respiration chamber that has the hole on top, or in the side of it, so that I can put an oxygen gas sensor and a CO2 gas sensor in at the same time. We have other options as well. We can do this activity with just the plain Nalgene bottle that comes with the gas sensors, and that would be if we were only doing one sensor at a time. And if you wanted to do some larger plants or even crickets or any other larger organisms, we do have a larger container too, that is our BC 2000. It's a 2-liter container. And this is great for people if you're doing like hissing cockroaches or certain reptiles, very small mammals. I would probably put nothing larger than a mouse in here, things like that. So to start the activity, what we're going to do is first take our peas, and I'm going to drain off some liquid. And we're going to take out about 40 peas. So when you're doing cell respiration with both the oxygen and the CO2 sensor, you want to have more peas than if you were doing just the CO2 sensor, because of the concentration of oxygen in the atmosphere is much larger. You're not going to see as dramatic of a difference as you would with CO2. So we want to add some extra in there just in case. The other thing you'll notice is I'm drying them off, because these are going to work best if we get the majority of the moisture off of the peas here. And by doing that, it helps decrease the amount of humidity that is actually going to build up in our respiration chamber.
Colleen, can I stop you with a question? We have a question asking if the peas were fresh and not frozen. Can you tell the audience a little bit more about where those peas come from and what you use?
Excellent question. So these peas started out as dry peas, kind of like the pea that you would plant in a garden to get a plant to grow. And what we've done is just soak them in water overnight. So if you are using, if you have fresh peas from a grocery store, those could work. You would not want to use frozen though, because frozen peas are, they're not going to be able to germinate because of the freezer damage that has been done to them. Okay, I'm going to add 40 peas into here. Very exciting, I know. Oops. Okay. So I have my 40 peas in, and what I'm going to do now is I'm going to stick my oxygen gas sensor in and my CO2 gas sensor in. And since these are Go Direct sensors, I'm going to turn the sensors on because they have the ability to do a Bluetooth connection so that we can connect them by Bluetooth to our device to do data collection. So I am going to share my screen now. Okay, and so what we're going to be doing here is we are going to do sensor data collection, and we're using our software program called Graphical Analysis. And Graphical Analysis is a program that can run on any device, be it computer, be it iPad, Chromebook, iPhone, anything like that. So I'm connecting my sensors here, and you can see I'm at my CO2, I'm connecting, and my O2, I'm connecting. And done. Now, just to make sure we can see this a little bit better, I'm going to change my mode here to presentation so we can kind of increase the view. There we go. Now, you'll notice when I've connected these that my carbon dioxide gas sensor is reading in parts per million, while my oxygen gas sensor is reading in percent. So what we want to do is actually change the units so that they are the same. So I'm going to click on the live reading over here. I'm going to change oxygen to PPT, and I'm going to go ahead and change CO2 to parts per thousand as well. And you can see we've already got data starting to go here. So I'm going to go ahead and press collect. And we're going to go ahead and have our first run of cell respiration taking place. So as this is happening, you can see that on the graph, we're going ahead and getting live data collection right away. Watching the peas themselves, you can see, is not the most exciting thing in the world because they're directly not really doing anything. But what we can see by using the sensors here is that there is active respiration taking place. We are seeing our carbon dioxide starting to increase, And if we look at our oxygen gas, it looks like a straight flat line. But if we were actually to zoom in on the data here by clicking on the magnifying glass, you can see that our oxygen level is decreasing. And I'm going to go ahead and do that for our CO2 as well. Now, the oxygen level is not decreasing at the same rate or at the same quantity as CO2, and that's purely because of the difference of the ratio of gases that we have in the atmosphere. Is that there's a lot less carbon dioxide in the atmosphere than oxygen. So we're going to be able to view and see those changes happen a lot more dramatically than we will with oxygen gas, just purely because of concentration in the atmosphere. Sarah, are there any questions right now?
There aren't from the audience, but could you maybe speak to why the bottle is tipped on its side? Is there a preference for how you orient the sensors during data collection?
Excellent. Yes. So the oxygen gas sensor has a cell inside of it that is filled with a gel that needs to be upright. So what we always want to do is whenever you're using an oxygen gas sensor, you always want the gas sensor to be sitting upright and never on its side, because that can actually affect your readings and not give you a really good, accurate idea of what the actual oxygen concentration is. The carbon dioxide sensor, it can go basically any direction you want to be using it. If I was doing just cellular respiration using carbon dioxide, I would still probably have the bottle laying on its side, purely because oxygen gas is more dense, and so it tends to gather towards the bottom of the bottle, and it would give us a better, more quick response in reading if we are having it on its side versus just standing straight up.
Great. And is that upright position, this is an audience question, is the upright position important for storage as well?
Yes, excellent question. It is important for storage. Whenever you get an oxygen gas sensor, when we send it to you, you'll have a box that has a label on it that says this side up, and that's how you're going to want to store it as well. If you do store it on its side, it can actually decrease the life of the sensor itself and its effectiveness. So that's one thing you always want to make sure is that it's being stored upright. It doesn't necessarily have to be in the box it came in. We store it here sometimes in a tub. As long as it's sitting upright, though, it is perfectly okay.
Great. And we have another audience question about the program that you're using, about graphical analysis. Where do students get that?
Oh, excellent. So Graphical Analysis 4 is like I said, it's a free application. And what I can show you here while we're finishing our data collection is on our website here. So on the Vernier website, you can download Graphical Analysis 4 for your computer. So if you go to Downloads, we can look here for Graphical Analysis 4. We go to More Info. And this is where you can get the links to download directly for Windows or Mac computers. If your students are using Chromebooks, they want to go to the Chrome Web Store in the Chromebook to download. And if they're using iPads or iPhones, they go to the Apple App Store. And if they're using Android phones, they would get it on the Google Play Store. Now, the thing to note is if your Chromebooks, for example, are being controlled by your IT department, students might not necessarily be able to download the app onto their own account. So it might be something that you have to ask your IT department to push out to the student devices. That way they make sure that they have the program and available for them to work on.
Great. And we have another question. Are the graphical analysis program downloads free for students? Their campus is using LabQuest.
Yes. The graphical analysis download is free, 100% for everybody. And you can use them with LabQuest units. You can actually use them with LabQuest 2s quite beautifully because you can do what we call data sharing with those. I'm not going to demonstrate that today, but that is something that somebody in the office can definitely talk you through because it's one of the, in my opinion, the best features of using graphical analysis with a LabQuest 2. Okay, so it looks like our data is collected here. And I'm going to just zoom to all my data by pressing that magnifying glass. And you can see that we definitely have some changes that occurred during our data collection. So what can we do to analyze this data? So one of the things that we typically want to know is what was the rate? So how much CO2 gas was being produced and how much oxygen gas was being consumed. So what we can do is we can actually just highlight a portion of this graph here. And I'm going to go to my graph tools icon. And from here, I can actually apply a curve fit, and I can apply my linear fit, and it gives me my linear fit equation here along with my variables in there. So we have our y equals mx plus b, and this is where we can pull in some nice math concepts here, is looking at the slope of the line, so m, and that's going to be able to tell us exactly, what our rate is, or the slope of the line. So we were seeing a increase of 0.008233 parts per thousand carbon dioxide gas production per second. And again, that slope is pretty small, and that's because we had to change the units to parts per thousand. And then we can do the same thing on our oxygen gas here. Apply our curve fit. And here we have a negative linear fit showing that the values were decreasing instead of increasing, but we are still seeing that change between the two. Now, the next step in this experiment, and I'm going to stop sharing and come back to here. The next step in our experiment that we do in this is we actually take the peas out of the chamber, and we're going to take these peas and actually put them in ice water. Because what we want to do now is see what the effect of basically ice water will have on our respiration values. At the same time, I'm going to be waving the bottle around a little crazily because what we want to do is actually get all of the residual gas that's trapped in this chamber and remove it out of there. Now, what's nice is because this chamber has two openings, it's a lot easier to vacate that gas. If I was using just the single respiration chamber, I would then fill this with water and empty it out a couple of times to make sure I vanquish all of the gas out of the sensor. At the same time, I'm also going to want to kind of get rid of the gas in my sensor here. And I'm going to kind of wave around my CO2 sensor and wave it kind of under the oxygen sensor to help extinguish any of the gas out of there as well. Okay, and then what we're going to do next is the same process, except this time we're going to put in non-germinated peas. So these are just the dry version of the peas. And we're going to just do the same setup again. Now, since we've done our first experiment already, students have some baseline data that they can analyze and look at and make a prediction of what they think is going to happen. So what we can do, I'm going to share my screen again here, is I'm going to go ahead and close out my linear fit. And what I might ask students to do is predict what they think is going to happen to our respiration levels here. Now we're changing it up, so we're no longer using germinated peas. We're now using peas that have not germinated. And so what we can do is go over here to Graph Tools. And what we're going to do is add a prediction. So we're going to draw a prediction just on the carbon dioxide graph here. And I'm just going to use the mouse. I'm going to click and drag what I think is going to happen. Ooh. You can see I'm not the steadiest of my mouse moving there, but so we're going to start like that. Going to save. And I'm going to do same thing with my oxygen gas. I'm going to add a prediction. And save that. And you can see the predictions have now shown up on my graph. And now I'm going to go ahead and put my sensors back into my chamber. Set my chamber up and go ahead and start my data collection. Now, I'm not sure if I really did a good job getting all the gas out of there, so we might see some changes in levels there, but we'll see. That's part of experimenting. And so if the students did see some changes in there, that could be for them to start analyzing and looking at a source of error potentially and have some explanations of what could have gone wrong during that experimental setup. Okay.
Right. Colleen, we have lots of questions.
Oh, fun.
First question, can one sensor connect to multiple Chromebooks at the same time?
Excellent question. So sadly, the answer is no. So the GoDirect sensors are Bluetooth and USB. So they can only connect to one Chromebook at a time. Now, if you have a LabQuest 2, that's where the benefit of that comes in, because you can connect it directly to the LabQuest 2 or now LabQuest 3 and then actually do some data sharing and share the data to multiple Chromebooks because of Wi-Fi.
Great. All right. So another question is, what is the optimum time for data collection, as in the minimum amount of time needed to get a good run for this experiment?
Oh, excellent. So you can see I'm doing the experiment for about 300 seconds or 5 minutes. Our protocol actually calls for you to do it for 600 minutes or 600 seconds, sorry, not minutes. 600 seconds when using the oxygen gas sensor. When using both oxygen gas and CO2, I tend to say 5 minutes is the minimum time. If you're doing just CO2, you can see results within a couple minutes. So I would probably do at minimum 3 minutes, but I still feel like 5 minutes is kind of that perfect ideal time for students to really kind of comprehend and see the changes taking place.
Great, thank you. And another question, if somebody bought their sensors in 2011, is it time to replace them yet? They have both CO2 and O2 sensors.
Okay.
That seem to not be giving them particularly accurate ambient concentration readings.
Right. So the CO2 sensors might still be fully functional, but they might be seeing a little bit more noise with them just because they are older. The thing I like to think about with these sensors is, especially when we're doing experiments like this, the actual value that the sensors are reading are not as important as seeing that change. So as long as you're seeing a change between the beginning and the end and students can analyze that, to me, that makes the sensor functional enough to do the experiment. For oxygen gas sensors, if they were purchased in 2011, they probably need what we call refurbishment, because that cell inside of them does go bad over a period of time and does need replacing. And we can replace those. It's about $100 for a replacement, which is a lot cheaper than buying a brand new one. And also, if your CO2 probes are just not holding a stable reading and are kind of reading all over the place, we are happy to get them in and take a look at them and see if we can do any repairs on them.
Great. And we have one more question right now, which is how backward compatible is the system that you're showing with older versions of LabQuest?
Excellent. So graphical analysis that I am showing with you will work with all LabQuest units. So it will work with the original LabQuest if you have it connected directly to the device. It will work with LabQuest Minis. It will work with LabQuest 2s. It will also work with GoLinks. The only thing that the program will not work with is any LabPro devices. So if you're still using the old Lab Pros that look kind of like a calculator, those, sadly, the USB technology on them is so old that it won't interface with this program. But the sensors you use with them likely will still work. Any sensor that can do what we call auto ID or auto identify itself is going to have the ability to work with graphical analysis just graphical analysis. You might just have to change what interface you're using or box that you connect the sensor to that will then connect to the device. All right, so we've now done our second round of data collection here. And if you're looking at my graph on the screen, you can see, oh, surprise, surprise. Our ungerminated seeds or peas did nothing. So we can very quickly move on then from this experiment or from this run of data collection and go right into our next run of data collection, which is now going to be looking at those peas that we had on ice. So we're going to grab our container, and what's nice is because we didn't really have any CO2 produced or oxygen consumed, I'm just going to go ahead and dump those peas out. We don't have to worry about too much. And I'm going to stick my hand in very cold water and pull out our peas. Now, some might wonder why we're not just putting the container with the peas on ice. And that's because the oxygen and CO2 gas sensors are not necessarily compensated for temperature changes. So the idea is that we want to just measure the respiration of the peas and not the temperature change of the air itself. So as I'm just going to dump out all the ice now, because that did not work as seamlessly as I thought. Yay for live experimentation. Okay, so I'm going to be taking my peas out. They're nice and cold and drying them off here. And we're basically going to do the exact same setup as we did at the beginning. We're just going to put them on a paper towel, dry them off, and let them go. Okay, dry them off nicely. You can't really see this. There we go. And we're going to drop them right back in our container here. And they're still very nice and cold. Now, I'm using what we call just basic garden peas in this experiment. You can use other varieties as well. We have often people will just use beans, so you can do different kinds of beans in there. You can also do other types of seeds as well, which I have displayed here in a second. All right, so looks like we're already seeing some changing happening here. So on our graphical analysis, let me share that again. And so you can see in my meters down here, I'm already seeing some changes taking place slowly but surely. So we're going to go ahead and start our next data collection. Now, if you're familiar with our software, you'll notice that I haven't had to do any data saving or anything like that. It just automatically, when I press collect, goes to the next rung in data. So what I can do while this is collecting, I'm going to click on my axes over here. And this is going to show my different data sets. And I'm actually going to go ahead and turn off my prediction. And I'm going to actually take the time right now and rename my data sets. So data set 1 here, this is going to be just my germinated peas. And then data set 2 is non-germinated. And then while data set 3 is going, I'm going to go ahead and rename that. And I'm just going to call it ice because those are my germinating ones that were on ice. And then I'm going to do the same thing. And then that carries over also to my auction one too. And I'm going to go ahead and turn off that prediction as well. What we can do is now also turn on all of our other data runs here. And we can get some comparisons going while we're doing our other data collection. And it might be kind of difficult for students to actually visualize and see the differences between the different graphs, so of what the different colors mean. So we can actually put on a graph legend here. And I should be able to move it over here so that we can actually see what the different colors mean. All right, here we go. So as this data is being collected, I can definitely already see a couple different things that are taking place. One is that this is growing a lot slower. It seems like the slope is a lot less when they were on ice versus when they just were germinated, kind of giving me an idea that, you know, ice definitely has a place here. What's throwing me off though a little bit that's interesting here is my oxygen consumption is actually going a little faster, which could be a couple things. It could be that at the beginning, I didn't give it enough time for the peas to actually really kind of absorb and take in more oxygen during respiring. So I'm seeing a little bit more there. And I would say this is the #1 thing that we see when people are using the oxygen gas sensor for cell respiration experiments, is that sometimes they just get some weird results with the oxygen sensor. And that's because that's kind of the nature of the sensor. It can be a little wacky sometimes. And often we recommend that when doing respiration experiments, I personally prefer to do them with just the CO2 sensor. Primarily because it takes out a complicated variable that might kind of throw students off with their understanding of cell respiration. Sarah, do we have any questions while we're finishing this?
Yeah, could you speak to what other types of treatments students might vary if you wanted to make this more of a lab exploration or an inquiry-based experiment? What could they vary besides temperature?
Oh, excellent question. So what I really like about this experiment setup is you can see in a very little period of time, we were able to basically do 3 treatments pretty quickly. And so this lends itself to really simple inquiry experiments that students can very easily do. And there's variables that you can change, such as the temperature. So we did germinated at room temperature, and then we put those peas in ice water as well. You can also have students use warm water. They can use different temperatures of water and see how that affects the rate of respiration taking place. What we can also do is look at, for example, pH. So instead of just having the peas germinate in plain tap water, we can have them be germinating in water with different pH levels. So you can try a pH 4 solution or a pH versus pH 7 versus pH 10. And the reason I use those three is because often those are the most common pH buffers you might have around the lab that are instant make buffers. Other experiments, and I'm going to stop sharing my screen for a second so you can actually look at me while I'm talking. Some other things that you can do is we can vary the number of P's, and then we can also calculate what the actual mass basically the amount of respiration that's happening per gram or per milligram of P. The same thing is we can use different seed types. So we can compare, for example, we have the ability here, we can compare radish seeds versus barley seeds. So you can actually look at monocots versus dicots. You can also look at different types of beans. So black beans, navy beans, pinto beans. And the thing that you want to keep in mind with if you're using different types of beans and seeds is some of those are going to take different amounts of time to really get the germination process started. The garden peas, we soak them overnight, but you can get a respiration out of them as quickly as 45 minutes of them soaking in water. So that can be really, really fast. For beans though, for like black beans, pinto beans, those might need to soak for about 2 days before you actually can see some results. And that's another open area for inquiries. You can actually look at what different soaking times does to that germination rate. Like what is the ideal time of soaking? Trying to think of other variations we can do. So numbers. And then you can compare organisms. For example, respiration rate of peas versus the respiration rate of a mouse or a cockroach or some crickets. You can look at respiration of mealworms. So you can do invertebrates versus vertebrates. There's pretty much an unlimited amount of inquiry activities that can go into this.
I have another question for you, Colleen. Can you do this experiment with aquatic organisms?
Oh, excellent question. So yes, you can, just not with these sensors. So the auction, let me go grab them here. So the auction and CO2 sensors here specifically are what we call gas sensors. So they are only to measure atmospheric gas levels. They are not waterproof. They cannot go in water. But we do have a dissolved oxygen probe that can be used to measure oxygen content in water. And that's what I would use to measure cell respiration levels for aquatic organisms. And you can use it for measuring fish. You can also do it with plant matter as well and do photosynthesis and cell respiration using the same type of plant matter. But dissolved oxygen is what you'll want to use, not either of these sensors.
All right, and Colleen, we have another audience question that came into chat. What is the best way to vary pH levels? Would you suggest combining acids and bases to get the desired pH or use pH buffers?
I think personally for the simplest setup for the teacher, I would do ready-made pH buffers. That's just going to, in my opinion, be a lot easier and in a way a lot safer to manipulate, especially if you're having the students make those solutions themselves. That's mostly what we use here is we have just pH buffer capsules where it's 1 capsule to 100 milliliters of water. And it's a really simple, easy thing to make up. And it eliminates a lot of kind of the hazardous danger of using acids and bases in lab. Now, if you're in a more advanced setting in like AP, IB, or college level, I'd say go ahead and have students make their own pH solutions. But be careful with it. Always a level of warning with it. All right, so what we're gonna do now is I wanna show a couple more features here for our cell respiration. So I'm gonna go back to looking at my data here. Now, The nice thing with graphical analysis, what we can do here is we can actually save this experiment. And if you're on a Chromebook, you can actually save this experiment directly to your Google Drive, and then students can access that data. So for example, if you are currently doing remote teaching or hybrid, where students don't really get to do a lot of experimenting hands-on, you can actually do something where you're, say, videoing yourself doing the lab, and then actually send the students the data for them to do the analysis with. We can also just do some screenshots. So I can actually export this as a graph image. So students can actually just drop the graph picture directly into a lab report. And we can also export this out as a comma separated value file to put into Google spreadsheets if we're wanting to, for example, combine a whole bunch of class data together. Okay, so speaking of having data available for students to analyze, what I want to show everyone is this option that we have that's available for everybody for free, because we know the weird situation everyone is in right now, and that data is not exactly something that you necessarily might have time to collect, since everyone's trying to figure out how all this works anyways. So on our website, we have this thing called Exploring Remote Solutions, that if you go to the webpage here, we have a bunch of solutions available for different grade levels. So we have them separated out. I'm going to just go to high school since that's where the majority of our participants are teaching from, but we also have K through 8 and college. And this kind of goes through all the different options we have. And we have a lovely webinar that we have the recording of that kind of walks you through a lot of these resources that we do have available. And we do have a mixture of free resources and paid resources. Let me show you. So some of the paid ones are the Pivot Interactives, which is basically it's a way to do kind of remote hands-on learning where students can change the variables themselves and actually basically look at videos of real experiments and analyze that data. But what I want to show you is our data library we've created. So we're going to go ahead and look at our free library. And this is something that we all put together here in the office, is we basically went through and found all the data we have for a variety of the different lab books that we have put out. And so by looking at the library, conveniently, biology comes up first. Yay for alphabetical listing. And what we can do here is what we've done is put a whole bunch of data samples up. So we're going to go to our cell respiration lab that we just did. It's from Biology with Vernier, number 11, CO2 and O2. And this is going to take you to a shared Google Drive. And what we have in this drive is we actually have the data available for students to analyze. And we also have the Word file of the lab activity itself. Now, with Google Drive, you can't just kind of double click and open a file that isn't a text file. So what we want to do is I'm going to right click on that and I'm going to download this data file. And so once it's downloaded, I'm going to go to graphical analysis here. I'm going to do a new experiment. I'm going to be bad. I'm not saving. And I'm going to go open a saved file. So I am going to choose my file, still not saving that file. And here I have my file in my downloads folder. And I'm going to go ahead and open that. And so once that opens, here's just the data tables, but I'm going to go and look at my graph. And I'm actually going to look at two graphs. So I have my CO2 and O2 experiments. And I'm going to look at just my germinating at room temperature peas, not my cold peas. Germinating room temp. Germinating room temp. And so here we have a set of data that's already been collected for this lab activity that students can now go in and do the analysis and essentially do the part of the lab that isn't necessarily the collecting of the data, but of the analyzing of the data. So that way students still have real data sets for them to analyze and look at, and have the ability to still kind of get some of that critical thinking in of looking at different data collection sets and how to analyze graphs and data information. Like I said, we have this available for all sorts of activities for all subject areas, not just biology. And you can just, these are all absolutely free for you. All right. Now, one other thing I wanted to show with graphical analysis is we have gone to another form of graphical analysis that is called Graphical Analysis Pro. And this was again in our remote learning solutions. So Graphical Analysis Pro is very similar to graphical analysis, except it's got some more advanced features. And this is a paid program. Right now, it's $69 for a site license for an annual subscription. And how Graphical Analysis Pro looks a little different is that it has this feature here that says See Experiments. And when I go to See Experiments, what we've done is actually uploaded some of these experiments that were in the data, our data library, except not only did we add the data in there, we've also added a video with it as well. So the students can actually follow along the video and see the live data collection that corresponds with that video as it's being collected. And my internet right now is not liking me. I'm going to just do the one that I've already downloaded. Maybe. All right. And so here I can actually do my replay. And I'm going to go ahead and start viewing the data collection. So it's the same exact process that we went through today. It's just now we've filmed it so the students can actually see the process taking place as well and actually have that video in time with the data that's being collected. So I'm going to speed this up a little bit. So that we can get this to go a little faster. And you can see it's kind of the same as before. We're just going through the same process exactly as I showed in the video earlier. Now, that's kind of one of the features. We're going to have more and more features coming through Graphical Analysis Pro. And like I said, it's the same app as Graphical Analysis. It's just got this little extra things, which is why we're starting to charge a subscription just for that one. Normal graphical analysis is still free and is going to be free.
Colleen, we have a question about the cost. Is the license per year or is it a one-time payment?
We are going to go per year on these subscriptions, and it's per department or campus. So it kind of follows the same line of what Logger Pro was like, where it's a site license. But instead of it being a paid once, it's now going to be an annual subscription. So it's $69 for basically the rest of the school year. I believe it kind of laps over July 1st.
Great. And we have another question. Can you review where this resource is again? And I'm not sure if that refers to the ESDL or Graphical Analysis Pro.
Okay. Let's let's do the data. I'll quick go through both. So to get to our experimental data library, you go to our front web page here. Well, it helps if I share my screen instead of just pointing at a screen that you can't see. So here we go. So on our homepage here, we go to Explore Remote Solutions. And then from here, you choose your grade level. So for this one, I went to high school. And this is going to give you all of the options for remote learning. So here we have, this is the information here about Graphical Analysis Pro. We have information of Pivot Interactives. For physics and general science, we have Vernier Video Analysis. And then here's the Analyze Experiment Data at Home, our experimental sample data library. So we're going to just view the free library. And then from here, we actually have a nice web video here for you can watch that actually walks you through how we imagine you would use it best in your teaching. We also have some nice quick start instructions here to kind of help you get going with it. But if you want to just see what's available, you just click on Browse Library. And that's going to take you to a spreadsheet that you can then look for specific book titles and then go look for specific experiments. Now, some of them are a lot more complete than others just because of what we had available, because this was something that we put together rather quickly to make sure you had something to get started with for the school year. So you can see we have some of advanced biology. Most of biology with Vernier is in there. And then we also have our two newer human physiology experiments books, and then our older physiology, along with ag science and some additional labs as well. For example, if we go over to chemistry, we have, again, quite a few options there. So it's just something that we went through and we kind of made sure we got what we would consider the most popular activities and labs that people would want to utilize in their classroom.
And Colleen, can you speak to the related videos that appear in that far right column?
Yeah, so these videos are ones that we do have available that we were able to still use and link to. They might not necessarily be the most up-to-date activities, and they might be with some different versions of the sensors. Oh, hey, of course I picked one that's about me. But they're there because, again, they walk through the whole experiment, and these typically were used more for resources for teachers to see how the lab was being done and how things connected, but it's definitely something that students can use to look at as well. And we're going to stop that. Any other questions?
Yeah, for Graphical Analysis Pro, is the cost for all of the labs that are currently in there, or is it just for a single lab?
No, that $69 gives you access to all of the labs in there.
Thank you.
Any other questions? Because we're nearing the end of our time here.
No other questions right now, but I'm keeping an eye on them.
All right. Well, everyone, hopefully you saw in the chat that Angie posted the link to the Google folder for today's activities that we did. And so in that Google folder, I made sure to put in the instructions for the biology with Vernier activity we did, along with the inquiry activity as well, so that you give some ideas for that. I also, I believe the data set is in there as well, the same data set that you can find in the experimental data library. So you don't have to search through the whole library, you can just go to that folder to use it there. And feel free to share that with your colleagues as well. At any time, if you come up with any other questions you have or need advice or any support through this time using sensors, especially in the time of COVID, feel free to contact us. Give us a call here at Vernier. We are working remotely, but we are available to answer your phone calls. And you feel free to email us as well. Biology@vernier.com is a great way to get a hold of both me, Sarah, and Dr. Melville, our third person of our biology department. And don't hesitate to let us know if there's anything that you need from us to give you a hand with. So if there are no other questions.
Oh, we have one last question, which is, are the previous workshops available for viewing?
Yes, great question. So all of these workshops edited and kind of made sure everything looks good with them. They'll be, I believe they're going to be posted to the same page you use to register for these workshops. So they kind of come up eventually. I'm not sure how quickly we're posting them, but I would imagine within the next week or so, you should start seeing them being put up.
All right.
Okay. Well, thank you everybody for spending this past hour with us. Hopefully it wasn't too boring with watching peas respire, because you know they aren't the most active organisms to use. So I hope you enjoyed it. I hope you got something useful out of this, and I hope everybody has a wonderful fall. Thank you.
All right. Thank you, Colleen. Thanks, everybody.